coordinate systems, and it's for us, believe it or not, for spherical coordinates. When you have spherical resistance and stuff, there is no magnetic field because the currents radiate out from the inner to the outer conductor in a way that there's no net magnetic field created. Okay, anyone at all? Y'all do them or not? How many actually tried it? You tried it? Did you have a question? Yeah, can you give me the specs on 4.8?
The infinite line one with the
Say it again.
A conductive loop in the XY plane is bounded by rho is equal to 2 centimeters.
All right, let me do that. So we've got the XY plane. Give me 1 second. And you've got Z-axis, a conductive loop from where to where?
From rho is equal to 2 centimeters to rho is equal to 6 centimeters, and phi from 0 degrees to 90 degrees.
All right, so you've got a loop like this. It goes from 2 to, did you say 6?
6.
All right, so it goes from 2 to 6 this way, and then it's 0 to 90 degrees? Okay, so it's basically like this. That's the conductive loop, right? And this would be an inner radius of A, outer radius of B. Here, A is 2 centimeters, B is 6 centimeters, and it goes from 0 to 90 degrees, or really from the x-axis to the y-axis. Do you all agree with this, class? What do they want now? H field on the axis?
H field at the origin,
Okay.
and you have 1 amp of current going in the positive A phi direction on the 2 centimeter.
All right. But positive A phi on what?
On the 2 centimeter.
All right, so it's going this way, I, and I is 1 amp, right? Correct? Is that right?
Yes.
Okay, now just take a look at this for a second and understand the problem, because I'm going to do this a little differently. You've got this crazy looking thing where you've got current flowing this way, then this way, then this way, and this way. Y'all follow me? So it's really 1/4 of, you might say, the XY plane has this in it. This is a good problem. What they want is the H field right here, right? They want that H field. Now, y'all agree with that? A couple ways to do this. If you look at this for a second, you're going to see 2 things that are apparent. Think about the current flowing this way and this way. Can they cause any H field at the origin? The current flowing this way and this way. Let me draw this thing. I'm going to look straight down the Z-axis. It'll be a little more apparent when I'm talking about it. So if this is the X-axis and this is the Y-axis, we have something that looks like this. If you think about it, this is the Z-axis coming out. And you've got current that flows like this. That would be the direction of current. Y'all follow me? Now, how would you get that value of the H field at the origin? A couple ways. Doesn't it look like really 1/4 of a loop twice? Right? But the thing to note is, if you look at the formula for H, or DH, from a differential current element, it's IDL crossed into AR over 4 pi R squared, right? Just remember what I'm showing you. I'm doing it for a reason. Now take a look at this current here and this current here. And take a look at this point. When you get IDL, it's in this direction here, right? And IDL would be in this direction here, right? What is the direction R here, AR? Isn't it in this direction, AR for that one, and this direction, AR for the upper one? You all see what I'm talking about? So what's the cross product, IDL cross AR? For this current right, and this AR, and this current here, and that AR. Class? You all see it's 0? This is the important point. So if it's 0, we can completely neglect that portion and that portion. You all with me? Now it kind of breaks down, because now, if you're taking a look at the H field from this portion of the loop and this portion of the loop, you can take a look at this And I'm going to do the inner portion right here. So when I look at IDL for the inner portion, that's the loop at rho equals, or at A, or A is 2 centimeters. I find out that the DH at the origin would be equal to IDL cross AR over 4 pi R squared. I'm going to leave it like that for a second. Now, next, I want to find a differential chunk of current here, IDL. So my IDL on the inner one would be equal to magnitude of I, and what would DL be? This is a really good problem. Think now. I'd be in cylindrical coordinates. Y'all give me that? What would DL be? The wiper arm length would be
80 feet.
rho, or AD feet, exactly, AD feet. Do you all agree with that? It's constant, so it'd be A D feet in what direction? Come on.
80 feet.
A feet, right? It's in the phi direction. Do y'all follow me on that one, class? It's real important you see this. This is moving in the phi direction, so it's times A phi. All right, that's the first part. I need my IDL. Now, what is R? Well, R is from here to here, correct, class? Y'all give me that? That would be R vector. So what would that be? Now think, you're in cylindrical coordinates, right? It's going to be what? R would be, you take the coordinates of the point the current exists that's creating the H field minus the coordinates of the observation point, correct, class? Or I should say, actually, coordinates of the observation point minus the value, the actual place where the current is creating it. I'm sorry, I said it the wrong way. So, if I want this direction here, it's going to be, in terms of rho, what's the value rho there at the origin?
0.
It's 0, right? And therefore, when I look at this, it's going to be minus A for this one times A rho. Is Z of importance to us, class? Z has no meaning, right? Because there is no variation in Z from here to here. They're both in the XY plane at Z equals 0. What about phi? Do we need to consider the phi values? Remember what I told you? If you're on axis, phi loses its meaning. Do y'all remember? Right? There is no phi point on the z-axis. It loses its meaning. We could go to Cartesian and talk more about this. So really, this is R right here, in a nutshell. And it should look, it makes sense, isn't it, class? Okay, now we have that. And when we do this, we see that DH for this one is equal to I, then DL, which is, I times A, D phi, A phi, crossed into AR, which is minus A times A rho, over 4 pi R squared, and R squared really is just going to be A squared, isn't it? Class? Hold on for 1 second. IDL, AR, my bad. It would be just that, my bad. It would just be in the minus A rho direction. Do y'all agree with that? Because to get AR here, you would take R vector over R magnitude. So R vector would be this, over R magnitude is A. It would just be minus A rho. Do you agree with that? And that would be a minus A rho. So then we go here and we find out that DH is equal to, all right, what's A phi cross A rho? All right. Think about it. I know this is, you don't use cylindrical coordinates enough. When you think about this, the normal way I tell people to remember this, if it's Cartesian, it's X, Y, Z, all these are plus. If they go the other way, cross product wise, they're negative. You've probably seen something like this in math. I don't remember if you did or not. Do you remember this? This is for cross products. If you do what? Rho, phi, Z, these are all positive, right? And if it goes this way, it's negative. Do y'all remember that? How many do? I'm curious. All right, and the easy way to get is your right hand, correct, class? Now, hopefully everybody here has a right hand. If you have your right hand, you take your index finger and put it in the direction of IDL, right? This is the way IDL, I've got it going this way, right? IDL in that direction, you gotta use a hinge thing. IDL cross R shows you the direction. Your thumb, it's IDL crossed in R, your thumb points in the direction of the resultant cross product, or H field in this case. Do y'all see that? And that's X, Y, that'd be in the positive Z direction. Do y'all see that? So it's in the positive Z direction for this one. You can almost see it here. Another way they say you can do the right hand rule for swirling currents. Anything that's swirling about, take your right hand and let your fingers grasp at the actual current's direction. Your thumb will point in the direction of the H field, positive Z direction. Can you all see that? You might have had that version of the right hand rule, but there's a lot of different versions. It all comes down to finding what the cross product will be in a right hand coordinate system. So if I look at this, that means this cross this will be minus AZ, with the minus is plus AZ. So I get I times A d phi in the plus AZ direction over 4 pi A squared. Now that's for the inner one, right? I'm glad you asked this. This is such a good problem. You all with me on this? Now I need to get the total H field. So what am I going to do with this? And this is just for this inner portion here. What do I do? From where to where? You're right. From 0 to 90 degrees, or pi over 4, correct? Or pi over 2, pardon. So now I take this and I say, therefore, H would be equal to, you'll notice everything in here is not a function of phi except for d phi. If you integrate d phi, you get phi, and you simply evaluate that from 0 to pi over 2, correct, class? And therefore you get this, I A over 4 pi A squared. We'll cancel that in a second. And then it's going to be times pi over 2 AZ. This would be for the inner one. One thing you'll note here, there's the A squareds and pi's cancel, and I end up getting I over, and then it's going to be 8 A. Y'all follow me? And that would be in the AZ direction. And this is for the inner loop. This is for rho equal A portion. Now, just taking a look at what we've done, can you all see how similar it will be out here, right? That IDL will have the same exact form as what we just did. Do you all agree with that? What's the difference, though, for the one out there? One difference. The sign of the H field will be opposite, right? The H field created by this loop, because the current's flowing in the opposite direction, will actually be negative. Do you all see that? As a matter of fact, what I can do is say, now for rho equal B, I can say the H field from that portion will be equal to, instead of I over 8A over there, I'm going to replace A with B. Y'all with me? And put a minus sign. It's going to be minus I over 8B in the AZ direction, and therefore H total at Z equals 0 would be equal to I over 8, and then it's going to be 1 over A minus 1 over B AZ, and that would be amps per meter. Y'all follow me on that, class? Is that the answer in the book? I didn't put the numbers
I
in.
don't think you posted the solutions.
Oh, please send me a message that I'll post the solutions for chapter 4. Somebody just did. A lot of you may have access to it already. I mean, they're all over the internet. I can only tell you that if you have a book and a solutions manual, somewhere out there, it exists on the internet. It doesn't matter what book it is. Even rare old books I found, somebody's got them, and they're there. And I'm not the best at finding them, but I can tell you this much. If I need a solutions manual for some book 20 years ago, I don't go and waste my time. I'll ask one of the students, and they'll bring it to me literally You want a PDF of it? You want me to print it? PDFs. Okay, you all with me on that one? I think, did anybody, can you confirm that answer? Anybody, this is 4-8, that's a good problem. Huh? No, they have solutions. I don't guess. You'll send me literally a snippet, how do they get that? I mean, even if I don't post, but if you don't have it, don't worry about it. Okay, do you all see that one? That's a good problem. Yeah.
Could you also find the solution by just, I think, if you take the magnetic field from a ring, could you find that by taking a quarter of the
You're absolutely right. He's saying you didn't need to do that integral. You can say if a whole loop has this much, if I take a quarter of that, then it's exactly right. It would be the field from one portion of that loop, inner or outer. You're absolutely right. It will be. I wanted to do it this way because, to be frank about it, you should see how to do it with an integration. Okay. Anything else? I want to do two other things, but that's a good problem. There was one problem I gave you that had a tightly wound toroid. All right, and I asked for the H field for that. This is a good problem, and this is a this is a Ampere's law problem that I ask about. I ask variations on this. What problem is it?
23, I think.
All right, if you take a look in your book, problem 23, in chapter 4.
Which page number?
This is actually called a Rogowski coil when it's used in the field, and it's used to measure the actual current flowing through a conductor without ever breaking the conductor, if it's an AC current. So here's the deal with this. They basically have something that's got a radius rho that's fairly large. And just think of this as like a PVC pipe. It's bent in the shape of a donut. In a radius rho, then they have something like this. And remember, think of that thing being just a circular hose. You went and turned on itself. You with me, class? All right, then this has a thickness. I forgot if this is A or B here, but you can tell me. It's got a diameter or a radius to that one. Y'all follow me? Now, here's the deal. What he does is this. He says, I'm going to wind a whole bunch of turns on here. And you can go ahead and complete that, but it goes all the way around. Think of it like this, all the way around. They're tightly wound turns. And you got N turns. And each of them, I mean, this turns, each of these things has a current I flowing in it. Y'all get the idea. So if you want, you can take a straight solid or a straight solenoid with N turns and just wind it around on itself and link it back. You follow me, class? And make a donut. Now, they ask you to find the H field inside here. So their goal is to find the H field inside this. And they want you to do it using Ampere's law. This is a little different problem. It requires you to think about this. This is not just a given. So how would you do it? First of all, it's pretty obvious that there's at least cylindrical symmetry in that plane that it exists, right? You with me? So what does Ampere's law actually say? It says the integral of H dot dl over any closed loop is equal to the current actually penetrating or enclosed by the loop, right? Now this becomes something that's real important. So imagine this in your mind. Just take a machete or something and sever that thing right down the middle so you get half of it above, half of it below, and look at what's left. So you would have this. Some inner radius, some outer radius. And then you would have a whole bunch of circles all the way around here that represent where you severed the wire, the inner wire. And you would have a bunch of circles out here that I don't care about yet. And there, where the return current is. Follow me? Current comes out of these. And you could just dot it. So that's the current coming out of the board, and then the current has to return. That's where the cross is on. With me? Can you all visualize that? Right. All right, now, this is tightly wound. Remember, what they're really trying to say is this looks like a current sheet. That's what he's getting at. It looks like it's a continuous current sheet where current's just coming up there. That's what his goal is, to make you think that way. Now, if I come around and I take, you all agree that cylindrical symmetry is appropriate here, right? It's obviously cylindrically symmetric. So now if I come in and I'm inside here, and I put an Amperian loop here, and I ask for the H field here, what would it be in Y? Tell me, based on that law.
0.
Why is it 0? You're right.
No current.
There's no current that goes through that loop. You'll follow me on that? None at all. Now, when I increase the radius of this loop, so that now I'm beyond rho. There's rho. Now I'm out here, and my Amperian loop is between the inner and outer radius that's really the thing that's holding all these terms. You all with me on that? So if you take a look at that, now if I'm for rho, I'm radial distance greater than, I shouldn't use rho here, I should use a constant, maybe call this rho m, the mean radius. Rho greater than rho mean, but less than the mean radius plus the actual diameter A. In other words, it's in between. All right, with me? Take a good look, make sure you see this. This is the kind of problem I like to give on quiz or on tests. Things like this, because it makes you think. All right, now, if you look at that, here's my Amperian loop, and I have the integral of H dot dl around that closed loop is I enclosed, or the amount of current penetrating this loop. How much current penetrates that loop? Each turn has I on it. How much? N times I. Do you all see that? Every time, every turn is going to cut through there, or it's going to go through here one time. So that means now I have Ni over here, where I is just an arbitrary value I choose. It may be 1 amp in the problem, but it makes no difference in terms of the solution. You all with me? What is the integral of H dot dl? Remember, the H field's a constant, right? Or we couldn't do this integration. So what is the integral of H dot dl? It's really H times the perimeter, right? What's the perimeter, or what's the circumference? 2 pi rho, exactly. So this is going to be H phi times 2 pi rho, or I can say H phi here is Ni over 2 pi rho. And you can say this is in the A phi direction, but it's not that important to say that. That would be the H field, and it would be for rho greater than the mean radius, less than the mean radius plus the diameter of that pipe. You all follow me on that? How many see this right here? And if you don't, then see me after class. This is important. Now, final question. What happens when I'm out here and my Amperian loop is out here? Now how much current penetrates that one in the plane of the board?
0.
You all see it's 0 because what's ever coming out is going in outside, right? So it's 0. This is real important. So if it's 0, the H field out here is 0. And in fact, it is. All right. This is a real thing. These are called toroids. Solenoids are straight tubes with tons of turns. Toroids are anything round, or that basically in a donut shape. Right? And they're both useful. Now I'm just going to say we're not going to go here today with this, but have you ever seen any type of power, or I should say current meter, where you just snip something on the wire, you don't break the wire? How many have seen that? The power company has these things all over the place. The way these things work is they have this, and they'll basically have the connection where it goes to the meter be between these 2 points, and this thing will be spring loaded, so they can open it up, they can put it on the wire, and the wire will be centered right there. Now, the deal is this. That current right there will create an H field that goes around here, and it will be time varying. And the H field will penetrate that loop, and it'll be circumferentially around. Then we'll get a time varying H field that we're going to show in a while, induces a voltage. The voltage is measured here. And if you know the frequency of the time varying current that created, the center current, you can deduce what the actual current is by the voltage measured. We'll get there. That's called a Rogowski coil, and they're used all the time for all sorts of work. Has anybody ever heard of that Rogowski coil? Power meter, current meter, any of these things? AC current meters?
Yeah.
The nice thing is you don't have to cut the wire. Now, if you want DC measurements, you do. There's no way to get that unless you have some sort of permanent magnet you can use to deflect the current would deflect the thing, and you can get a measurement that way, but deflect the magnet. Okay, that's the second one. Any other questions? Great question, though. This is a good question. First one's a great question. All right, I'm gonna do one more of the plane, and then we'll talk about I'm hearing about the weather today. The best way to say the weather forecast is it's uncertain. Could be bad, could be good. I hope I don't get wet going in my car, because I didn't bring an umbrella. But anyway, now think about Ampere's law, the way we've applied it a couple of times. Suppose now, this takes a little imagination. We've got an infinite plane, and I'll try to draw it here first. An infinite plane, infinitesimally thin. Think of aluminum foil, just rolled out. And it's going to be infinite in both directions, but now we have a certain current going down here. Now, and this is a surface current. Y'all follow me on this? It's going to be a current. So the way a surface current is defined would be amps per meter. Y'all follow me? And the symbol is K. So normally they say I have K, it's a vector, amps per meter here. And this K would be in amps per meter. Now if you look at that, that's an infinite plane in both directions. Y'all follow me? Infinite plane. There surely has got to be some symmetry we can exploit to find out what the H field is above and below. Do y'all agree with this? So now what I need to do is take this infinite plane and look at it straight down an edge. So I got something I can work with here. So if I look right down an edge of the infinite plane, here, and I'm going to say the current's going into the board. So I'm just showing you that the actual surface current, which is K, it's an amps per meter, is all into the board. You all with me on this? Just get a mental picture of this. Look down the edge. Remember, it's not I anymore. I loses its meaning. It's infinite. It's got to be so much I per meter. All right. Now, I'm going to do this. First, you all agree there's a large amount of symmetry here we should be able to exploit. So now I do this. I create an Amperean turn like this. And I'm going to say this is my Amperean turn. You'll notice it's rectangular in this case. It's going to have a height h, and it's going to have a length L. And the way it works is I'm going to make the claim that the H field above here will be the same in magnitude as the H field below there. Do y'all grant that to me? Based on arguments of symmetry. Furthermore, I'm going to say because this is infinite, it doesn't matter how far up I am, it looks infinite, right? Therefore, I can kind of deduce this. This is a weak argument, but it's true. H field will not be a function of how far I am away from it. Y'all with me? If it's infinite. All right, now this is my Amperean loop, and here's the direction. I'm going to say the H field this is the actual path direction. So, just bear with me on this one. If I take the integral of h dot dl around that closed loop, I know that's going to be the I enclosed, or penetrating that loop. Do you all agree with that? I'm going to talk you through this one, and I hope you can see this. Just think about what I'm doing. But to make this a lot easier, what I'm going to do is, I'm going to say h dot dl, but I'm going to take the limit of this as h itself goes to 0. So I'm going to shrink these things down so they're just a little bit above, just a little bit below the actual current, surface current. You all with me? I'm doing it because I don't want those sides to get in the way of this calculation. So when I look at this, well, h dot dl here, that h field's a constant. It's really just going to be h phi, right, times L above, plus down here, it's going to be h phi times L below is equal to I enclosed. How much current would be enclosed here? Remember, K is a surface current. It's amps per meter. L would be in meters, right? Do you all agree it would be K times L? Right? If K is in amps per meter, L is the actual length of this loop in what, right, the horizontal length. It would just be K times L. And K is a surface current times L. When you look at this, you see the L's cancel, and you get h phi is equal to K over 2 in magnitude. I'm going to tell you how to get direction in a second. Do you agree with that? And this is nice. So if you've got a thin sheet, and you know the surface current, that's approximately infinite, you can get the H field's magnitude above or below that sheet. It's simply the K value divided by 2. The direction is something your right hand gives you in a heartbeat. So, with the right hand, this is nice doing this stuff with, if you're using Ampere's law problems. It's a bit inexact, and we can mathematically state it in a much clearer way, but based on, I'll just tell you this much. You take your thumb, you put it in the direction of K. If you have any infinite surface currents, your fingers will move on your right hand in the direction of the H field. Above it, it's going that way. Below it, it's going that way. You all see that, class? Everybody's got it right. You just take it, you know, current's going into the board. Follow me on that? Current density, I should say. It's surface. In that direction. H field above going that way, H field below going that way. You all see that? That's a simple, I guess, mathematically unrigorous way of figuring it out. Rigorously speaking, in Weber's book, he does this, but to do it rigorously, you have to get something called a normal vector to the plane. And this is in his book. And then you can say H field above or below the plane. This is for an infinite plane only. Is going to be I, and it would be, really it's going to be K, pardon me. K crossed into A normal over 2 will always give you the vector direction and magnitude of the current. Remember, K is a surface current, A normal is a normal direction, and over 2. Now, I'm going to just say this. If we went and put a little, if I gave you something with a little more meaningful problem. Suppose this is my plane. This is the X, Y, Z coordinate system I'm using. And in the XY plane, I had a value K is equal to, say, minus 5 AX amps per meter in that plane. Now just think about it. Minus 5 AX, if AX is in that direction, minus 5 AX would be in that direction. Magnitude of 5 in that direction. With me on that? That's amps per meter. All right, now if this is where it is in that plane, if I'm above the plane, what is AN? If I'm above, what's a normal unit? It's got a magnitude of 1 It's perpendicular to that plane if I'm above the plane. Anyone?
Easy.
Y'all see it's AZ? Sure. It's gotta be AZ if I'm above the plane. All right, now take a look at H. Based on what I've showed you, it's going to be AN, right? Oh, actually, it's gonna be, sorry, I or K crossed into AN over 2. K is minus 5AX, I'll forego the units here, crossed into AN, AZ over 2. I got, AX crossed into AZ is minus AY, but there's a minus sign plus AY, so it's 5/2 AY amps per meter. Now just take a look at that and see if that makes sense. You got a right hand, right? Current going into the board, thumb in the direction, your fingers point in the plus Y direction, right? That jives, doesn't it, class? Y'all see that? Normally when I do these problems, I don't write that down. Just look at my right hand. It's going there. I know it's, if I'm above the plane, the H field's in that direction. If I'm below, it's going that way. And that's the way I do it. You with me, class? Now here's the other thing too when you're doing these problems. Because these problems are linear problems, these are for linear materials. If you had a current sheet above and a current sheet below, and say this current sheet, the actual current was going in, and this current sheet is coming out, then what you could say is, I know that if they're the same magnitude currents. In other words, it's like a differentially driven, very flat, long transmission line of sorts. Follow me on this, guys? If you knew K there, it's going that way, it's going in. I know the H field from this one, if this is K going in, and this is minus K coming out, then the H field from this portion right here would simply be magnitude of K, whatever that is, over 2 in that direction. Do y'all follow me on that, class? This one is going to be magnitude of K over 2 also, or the actual H field in here is K in magnitude, in that direction. With me? But what is the H field above here? It's 0. There's perfect cancellation. Y'all with me? And the H field below there is 0 as well. Now, some of you may see this. They'll have, at times, transmission lines that are very wide relative to the height, almost like a capacitor kind of thing. The reason they do that is that the H field above and below that is 0. It's a very low impedance transmission line that I'll spend more time on later. I'm just telling you about some of the things that you'll actually be able to figure out in terms of what the H field is based on Ampere's law in the real world that you'll come up against. Okay. Those are the things I wanted to cover today, dealing with magnetic fields. So now for the test. Everybody, do you have any specifics about the test you want me to answer? Why don't you write this down? For the exam, please bring 2 Smith charts. Put your names on them. Don't have anything else written on. We're going to have a Smith chart problem, obviously. There will be at least 1 Smith chart problem, but bring 2 in case you mess one up. Something you're familiar with. Make sure you bring a charge calculator, a straight edge, and a compass. Good compass. Then, we could do a Smith chart problem if you want me to. You can pick one out for me, but it's going to be some sort of matching problem. All right. It's going to be either series or shunt stub tuning. Now, we've done a bunch of those, right? So, series or stub tuning, and I'll go a step farther. It will be with a shorted stub. All right. Short, so I'm not going to give you open because I don't like them. They're not used. If they are used, I'm not familiar with the time they'd be used, because anytime you got that, you're asking for trouble, in my opinion. It's an antenna. It's a disaster. Anyway, so you're going to get that. you're going to also get things that deal with, obviously, capacitance and resistance based on the electrostatics that we've talked about. Write down Gauss's law, write down Ampere's law. And I'm going to just mention one other thing. I don't think I would give a transient problem on this exam. So I would not spend a whole lot of time on transients. But the other things you need to know well. Remember how you get the standing wave ratio. Remember all the things pertaining to the use of the Smith chart for matching. All right? And I will ask you to either minimize the distance, or the distance, the length of the stub, or the length from the device you're matching to the stub's connection. One of the two, and you remember the tricks with that. It's been a while since we've done that. For electrostatics, honestly, Gauss's law is real important, but you still need to be able to understand how to get the electric field from a point charge, from a line of charge, from a plane of charge, or from a loop. You've got to know that, and you should know how to get the H field from any of those geometries as well. So E and H for the common geometry, D, E, and H from the common geometries. All this is based on the homework, by the way. If you look at the homework, this is what you were inundated with, and on quizzes. If you look at your past quizzes, it's based on that. You do need to know something about circuits in terms of parallel and series connection. Remember on that quiz I gave you, the two capacitors added as if they were in parallel, or just C1 plus C2 once you got the right value. But the resistances were in parallel, so it was 1 over R1 plus 1 over R2. A lot of people didn't do that. They just added R1 plus R2, and that's wrong. So please make sure you understand basic things like that. I don't think of anything else. I'll have to be asked, do we get a formula card? No. But you know how you've got the impedance of a transmission line? I'm going to write this to know you. If you have just a transmission line like this to a load here, ZL, and this distance here is L, and this is Z naught, right? And you should know how to do the complete circuit. That was a problem that we did, where you actually had like an impedance here, then you had a voltage source. As a matter of fact, I might as well just draw that up. If you have a source impedance and you have a voltage here, say V source, and you wanted V load right here, or the power at the load, it's given distance L. Remember, down here, Zn, I'll give this to you, the input impedance to a transmission line would be Z naught times ZL plus JZ naught times tangent of beta L, beta is 2 pi over lambda, right, over Z naught plus JZL times tangent of beta L. I wouldn't use a lossy transmission line for this kind of thing. And beta, of course, is 2 pi over lambda. And L is the length. Do y'all remember that formula? All right, I would give that to you. I don't expect you to memorize it. I'm going to warn you about this formula. People make mistakes with it all the time in their calculators. I think I've warned you about it before. Trust me, you need to run this through a few times in your calculator and make sure you can do these calculations, because the typical problem is right here. Beta L would be a radian value, 2 pi over lambda times L in lambda, like it was lambda over 5 or something like that. That is 2 pi over 5 in radians, not degrees. Do y'all follow me on that? So make sure you would use the radian operation when you take the tangent, not the degree. That's a common mistake. There's probably a few other mistakes, but those are the ones I can think of. So it's comprehensive, but my advice to you, if I was sitting where you were, look at the homework, make sure you don't have any concerns about doing that homework in a seamless way without struggling, and the quizzes. Look at your past quizzes. Any other questions? Any questions at all? Yeah.
Will you give us any formulas we need, or we need to memorize formulas, or a little bit of both? Or besides
That's the formula I give you.
That's the one.
Yeah, I mean, I'm not gonna ask you some crazy stuff, all right? I'm just, if you have to know basic stuff, right? Like Ampere's law, things like that, you've gotta know. You gotta know that kind of stuff, the basic things for loops, line charges, things of that nature. And remember what parallel and what series mean in terms of adding things. How many made a mistake on your quiz based on that resistance being added the wrong way? I'd say it's over 50%, because I looked carefully at that and I remember you got the right value of R1 and R2, but boy, then you added them. I mean, mathematically added the numbers together, and that put them in parallel. They were in parallel, not series. I don't know how many people got 10s. I'm gonna say it's about maybe a third, fourth to a third, but there were enough people that should have got a 10 if they only paid attention to how you add resistors. It bothered me. I thought I really went over that the day before, but I guess I didn't. Any questions? Bless you. I'm gonna be in my office right after class if you got questions. Tomorrow, I've got a full day. I teach from 9:30 to 10:45. I take some candidate to lunch. I've got a meeting from 2 to God knows when. So you're gonna ask me about my availability, and frankly, it's gonna be sparse, because I've got too much on the plate. But you can always send me emails, and I'll try to respond to that. I'm going to my office right now. If you got major concerns you wanna ask me about, now's the time. Anything else? I wish I could tell you more. Oh yeah, if you are gonna bring any snacks or anything in here, I don't mind.